All right, calculus, we are looking at AB 37 here, which is the natural log function and focusing primarily on differentiation. So let's see an interesting relationship here between the natural log function and its derivative. So this is what I want to look at. If you were to type in this into your y1 in your calculator, and then you set up your table, your delta x equals 1, meaning that it's going to count every 1 for your x inputs here. And, excuse me. All right. We can actually calculate the derivative of each of these at stepping points. So that's all it's doing here. It's saying here's x and here's the derivative of natural log of x. It's taking that x and plugging it in. So what happens? Okay, so this first one, that's 1. Now, it's a lot more evident if you write these as fractions, and that's kind of, cluing you in here, like with the 0.333 thing and stuff like that. So let's see what would happen if we were to write these as fractions. The second one here would be 1/2, and then we got 1/3, and then 1/4, 1/5, 1/6. Ooh, pattern. Lots of pattern. So the idea is that the derivative of the natural log of x is 1/x. Okay, so that's the basic. And the basic is always easy to kind of identify and define and even remember. But what we want to look at is, what are all the details that go on with this? Because we know, for example, that this x is just a basic function, but what about that whole chain rule kind of layers thing? What if that wasn't just x? What if it was like natural log of x squared? What would happen? Well, let's take a look at that. Here's the general idea. Here's the basic, natural log of x, 1/x. Here's the more common application that you will probably see, and it's the natural log of u. Well, we have that 1 over that original piece, but then we're going to multiply by the chain of the inside here, the derivative of that inside piece. Now here's something that's kind of different, and a lot of people don't really kind of catch on to this at first, but eventually they do. So your original function has the natural log symbol here, the function natural log, but then the derivative, there's nowhere is there a natural log. So that's, kind of interesting. A couple of notes here. These are very minor details, but they matter a lot when you're trying to clarify your concluding answers. If we don't define u on the inside as some type of positive number, you cannot take the natural log of a negative number. That doesn't work. But here, if you were to say absolute value, then you could do that as long as the inside, you can't take natural log of 0 either. That doesn't work at all. We can get rid of negatives by doing an absolute value right there, but in general you can't really get rid of the 0. So let's look at this first one. I look at it and I see a couple things. First of all, the inside is not just x, because we already know the answer to that one, and that's not what it is. It's got an inside layer, and if I were to think of this as a u equals 4x, then the u prime, or du dx, you could say, let's get rid of this little prime here, du dx is 4. So y prime then, if I'm to follow these steps, is going to be 1 over u times du dx. So 1 over u, that's 1 over 4x, times du dx, which in this case is 4. And that would simplify, the 4's simplify, and we do just have 1 over x. So that's kind of interesting too. And that's actually a consistent pattern. When it's just a constant multiplied by x, this would be your derivative. And, interestingly enough, you could have predicted that if you separated this into natural log of 4 plus natural log of x, because with log properties we can split a product into addition of 2 logs. And this first term is a constant, and derivatives constants are 0. Then it'd just be derivative natural log of x. Okay, so Constant multiple rule kind of has a different, place here where it kind of simplifies itself out. Let's look at these next ones. Let's get some vertical bars in here. It gives some defined space to work in. There we go. All right, so how about blue? Blue looks good to me. We have an inside layer again, so this time u would be x squared minus 3, and then du dx, that's going to be just 2x. So now when I'm trying to find y prime, which is really 1 over u times du dx, pretty consistent with this pattern here, it's going to be 1 over x squared minus 3 times 2x. Now, of course, you can simplify this, and most likely you would see it simplified. It would say 2x over x squared minus 3. They combine these two fractions into one product, with just one numerator and one denominator. Okay, now these next couple, you can probably start seeing the pattern, do a little bit of predicting, and just looking ahead. So I look at this, and here is my inside. Well, I know that y prime is going to have, or the derivative, I guess you should say, of y. The derivative of y, it's going to have 1 over that piece, which in this case is 3x squared minus 5x plus 8. And then the derivative of this, well, the derivative, it's just a polynomial, so I could do that one in my head, not too bad. The first term is going to be 6x, and the second term is going to be minus 5, and then the 8 goes to 0. So there's our two pieces. Now, again, simplified one numerator, one denominator, 3x squared minus 5x plus 8. Check. Move on. Okay, now we got some interesting stuff. I'm actually going to show you kind of two different ways to do this. Let's start with what we've been doing here for a few of these, and we have an inside function here, x, and it's a square root of x, so I would think of that as u equals x to the 1/2. That would mean that du dx would be 1/2 x to the negative 1/2, or even more simply, 1 over 2 square root of x. So that's the derivative. The original is square root of x. So if I'm saying y prime equals 1 over u times du dx, let's see how these pieces would fit together here. We'd have 1 over square root of x times 1 over 2, looks like, 1 over 2 square root of x as well. Now simplify this even more, and the square root of x times square root of x is just x, and the 2 stays in the denominator. So we'd have 1 over 2x, because these two x's multiplied. Square root of x times square root of x equals x to the first. Okay, that's really not that hard, but look at the advantage now of doing some algebra first. Let's say that I called this natural log of x to the 1/2. Then I said, oh, power rule. I can drop that 1/2 out front. Then I have 1/2 natural log of x. At this point, this constant, I can treat it with that constant multiple rule where it just kind of tags along. So y prime is just going to be 1/2 times the derivative of natural log of x, which is 1 over x, or, put together, 1 over 2x. So whether you want to do algebra first or later, whatever algebra you can do first often simplifies derivatives and integrals with natural logs. But, it's really not that hard to follow it the other way as well. Okay, let's, of course, increase the complexity here. We're going to do some combo plays. So we got 5 sets of rules: power, product, quotient, trig, and natural log. Okay, so let's just kind of work our way through this one step at a time, but I want to plan for each one. Here, let's give ourselves some vertical bars. Begin to work around. Kind of organize this work. Alright, there we go. This first one, I see two functions. It's really like an a times b, which means I have a product rule that I got to deal with. I also have to deal with this, we got the power rule in there, which is almost super easy, not even worth mentioning. And now this new natural log one to work around. So since I'm doing a product rule with a and b, I know that y prime is going to be one original times the other derivative plus the vice versa of that. So a or b times a prime. There we go. So I need to know what a prime and b prime is. Well, in this case, a prime is 2x because it's just x squared for a. And then b prime, well, b is natural log of x, and the derivative of that is 1 over x. So let's just fill in the pieces. We would have ab prime, so that's x squared times 1 over x. Looks like some of that's going to simplify. And then the second half here, we would have 2x times natural log of x. Not too much craziness going on. Let's see if we can put some pieces here. This squared and the x in the denominator just becomes x. Then we have plus 2x natural log of x. Okay, that looks great. I really like how that looks. Just to kind of predict what people might do on a multiple choice test or try to trick you into making it look slightly different. I noticed that I have an x in common for each of these, so I could pull that out. And that would give me 1 plus 2 natural log of x. And then they could even take it further, and this would just be kind of silly to go this far. But you could say 1 plus natural log of x squared, like that. So you could do that. Do you have to? No. But I just want you to see that there are multiple versions of answers here, and as long as you have one or you understand the relationship between them, you're fine. Okay, now what do we got? We got quotient rule, and of course we're dealing with natural log all today. So natural log of x, we got to deal with both of those. Okay, so quotient rule, that's not too hard. Y prime is, we got the low d high minus the high d low all over the low squared. So I need to figure out what d high and d low is, the derivative of high and the derivative of the low. So what's the derivative of the top piece? That's just 1 over x, because it's log of x, natural log of x. And d low, that's almost too easy. It's, again, hard to give it time to mention, but derivative of x is just 1. Okay, so let's fill in the pieces. Y prime, low d high, that's x times 1 over x, minus high d low, well, that's natural log of x times 1, so that's done. And then we got over x times x, or x squared. Simplified, these x's would simplify, so we'd have 1 minus natural log of x all over x squared. Alright, so there we go. That wasn't too bad at all. Now, for this next one, it's so similar, but notice that these two pieces are switched. So I could just say my d low is 1 over x, and my d high is 1. And I'm just going to kind of switch around some pieces here. So low d high, this time, is going to be the natural log of x, minus high d low is going to be the x times 1 over x. And so it's kind of like those two pieces switched, and these are actually going to simplify on the other side this time. One other slight difference here is we would have natural log of x. Okay, now this is something worth mentioning. Natural log of x squared. You need to make sure that you don't do simplifying that's not allowed. So for example, natural log of x squared is not the same as natural log of x squared, like this. Those aren't the same thing, and it kind of has to do with order of operations and squaring and doing a log and how they have different patterns in them. They're not the same, which also means that it's not equal to 2 natural log of x. Neither of these, this doesn't connect to either of those. Even though these two on the right here are the same, neither of them would connect to the log of x version on the left. Okay, so simplified all the way, natural log of x minus 1 over natural log of x, all of that squared, and y prime. Done. Okay, what do we got now? Chain rule. Chain. How do I know it's chain? Well, a couple of reasons. I see an inside here, and I see an outside. So let's work our way through the outside first, and then to this second layer, natural log of x. So y prime, outside layer first, 5 times something to the 4th. Well, that something is natural log of x. and then I have to take the derivative of that, which is 1 over x, based on the earlier relationship we saw. So simplify it into one big fraction here. We'd have 5 natural log of x to the 4th power over x. That's it. Super easy. Okay, so combo play is not that big a deal, but of course, you know, it always gets a little bit harder. So now we have these, when you start throwing trig and, you know, powers that aren't really looking like powers, like this first one, that's when a lot of people kind of freeze up. But it's really the same rules you've been working with the whole time. No big difference here. So let's start with the first one. How about orange? Okay, so I'm first going to call this... Ooh. Oh, I got to take it off that vertical line. That's why it's not right. There we go. This is going to be natural log of x all to the 1/2 power. Again, you can't drop that 1/2 because this is different. It's natural log of x all to the 1/2 power. The 1/2 is not connected to the x. It's connected to the whole term. So it's really a chain rule. You know, I got an outside layer and an inside layer. And of course, we have the natural log to deal with here as well. So let's start out with the outside layer. It's going to be 1/2 times something to the negative 1/2. This is actually very similar to 8, except we had to translate the radical to a power. That leaves the inside natural log of x and the outside 1 over x. Okay, so there is a little more simplifying with this one. For example, this negative 1/2 power means it's going to be a square root in a denominator. Then we got a 2 in the denominator and an x as well. You know, let's squeeze that x in front of there. So we would have 2 and an x, and then we got natural log of x. What's left on top? Actually, just the 1. So there we go. That's what that would have been. Next, here we go. How about blue? So layers, chain. Got to deal with the chain. So outside is cosine, inside is natural log. So when I do the derivative, start with the outside layer. Eat your way through that candy shell, but don't eat the chocolate yet. So the outside layer cosine becomes negative sine. And then we leave the inside alone the first time. Then we're going to multiply by the derivative of the inside, which in this case is 1 over x. Put it all together, we get negative sine, natural log of x, all over x. Simple. Next one. So what's the difference here? This one is so close in structure. Just the two pieces are swapped, but it makes huge difference in derivative. And here's why. Because you would think of this like a chain, but it's a chain natural log. You know, and I'm putting a little hyphen there because it's really kind of its own thing in some ways, because this natural log is more like a substitution rule, like natural log of u, which we dealt with at the beginning. And so y prime then is just going to be 1 over u times du dx. So let's work that out. U in this case is cosine, so it's going to be 1 over cosine x. And then for the second piece, it's du dx. What's the derivative of cosine with respect to x here? With cosine of x? That's going to be times negative sine x in a numerator, of course. So put it all together, we'd have negative sine of x over cosine of x, when that's going to equal negative tangent of x. You might not expect that, but be prepared for it. You know, it's often common for trig values that, or trig functions I should say, that can be combined into less writing, often are. Okay, keep on going here. We got y equals natural log of x. Oof, that's messy. Well, let's document every little thing we're doing here. So I'm going to look at this as y equals natural log of u, which means to me that y prime is going to be 1 over u times du dx. Okay, so that's where I'm at so far. Now, considering what we have here, the u is actually this piece inside. So u equals natural log of x. And du dx, that chain piece that's going to be attached, is 1 over x. So when I'm looking at y prime, we start with 1 over u, so that's 1 over natural log of x, times du dx, which is 1 over x. We put it all together, we'd probably write this x out in front. We'd have 1 over x natural log of x. That'd be your simplified version of this. So keeping moving here, let's take a look at the next one. Now you're going to see why those rules, that whole algebra first thing, might have been a little helpful. So first, using a product to split into sum or quotient to split into difference or power, and we can drop the power out front. So let's look at this. For number 13, the hard way. There's really two ways that we can work our way through this. There's the hard way, and I don't know if it's necessarily the easy way, but probably a little bit shorter. So the hard way would be keep this inside defined as one function. And in this case, a multi-layered function because it's got an outside radical and an inside polynomial. It's a multi-layered function, multi-layered u. So u equals x squared plus 2x minus 3. And I'm even going to do this. I'm going to make it a little simpler by writing that to the 1/2. Then du dx, the chain, the derivative of that that's going to be attached, is 1/2 x squared plus 2x minus 3 to the negative 1/2. So there's the derivative of the outside times the derivative of the inside, which in this case is 2x plus 2. Now there would be some simplifying going on. So 1 over u times du dx, let's see how this would work out. Because y prime, remember, is 1 over u times du dx. So what would we get? Well, it's saying find dy dx. Let's go ahead and write it like that. Same thing as y prime, dy dx, which equals y prime. We got 1 over u, so that's 1 over x squared plus 2x minus 3 all to the 1/2 power times du dx. And now keep in mind, this negative 1/2 power means that's going to go to a denominator, so we're going to have 1 over 2, and we got all this stuff to the 1/2 power, times x squared plus 2x minus 3 to the 1/2. And then up top we have the 2x plus 2, the du dx. So I really combined these two into one fraction there. Okay. So what happens here? I notice a couple of things. I see that I have the same thing here times itself, and so that means it's going to be squared. And that's kind of like saying square root of something times the square root of the same thing is just itself. So I look at those two pieces, and then that tells me I get x squared plus 2x minus 3. And then we got this times 2 on the side. Then we have this 2x plus 2 in the numerator, 2x plus 2, which is really, if you want to think about 2 times x plus 1. So then we'd have 2 times x plus 1, and then you can simplify these 2's. I know that that's doable, but man, there is an easier way. And here it comes. So the easy way, this is doing algebra first. It's just manipulating the equation to get it to an easier format so that when you take the derivative, you have fewer layers to deal with. So what we're going to say is y equals x squared plus, pardon me, we need the natural log in there. Natural log of x squared plus 2x minus 3 to the 1/2. Then we're going to drop that 1/2 power out front. That gives me 1/2 times natural log of x squared plus 2x minus 3. Now, I don't know if this seems easier to you, but I look at this u layer, the inside of the natural log there, and it's a single layer. Because it's a single layer is easier. We've removed the outside layer by making it a constant out front. So now y prime, I'm looking at it, we're going to have this 1/2 times natural log, the derivative of this is going to be 1 over u times du dx. We have that 1/2 out front. So we'll still have the 1/2. 1 over u is going to be 1 over x squared plus 2x minus 3. Then we got the derivative of that on top, which is 2x plus 2. And we saw earlier that we could factor out this 2, simplify that if we wanted to. But here's the idea. I wasn't really doing any complex chain rules. I removed all the outside layers by doing the natural log algebra, the manipulation there. And that's really what's helpful. Okay, let's do this last one, and you'll see how this is even more helpful here. So when I look at it, I see a couple things. So for one, I would originally think, oh, I got to do a quotient rule. Oh man. So you'd see this high and low, and you'd want to do a quotient rule. But I could change it to y equals natural log of x squared minus natural log of 3x minus 2. How did I do that? Well, it's the quotient separation here, like number 2. So how does that help me? I could even go further. Look at this. I could take this power, drop it down. I'd have 2 natural log of x minus natural log of 3x minus 2. Now if I'm thinking about derivatives, y prime dy dx, the derivative of y with respect to x. For the first term, I have this constant multiple, so that stays. The derivative of natural log is 1 over x, which would just be 2 over x if I simplified that together. For the second one, we're seeing this pattern, and hopefully at this point you can abstract a little bit and kind of do some in your head, I guess you could say. It's really 1 over this piece here times the derivative of that piece, or the derivative over the original, you could say. It's like the derivative over the original. And the original in this case is 3x minus 2, so I'll put that on bottom. The derivative of that is just 3. So it's that easy. 2 over x minus 3 over 3x minus 2. Now, of course, would they manipulate this, make it one big fraction or something? Maybe. I don't know. Maybe. I'm not saying they would. I'm not saying they wouldn't. It's possible. But we're going to leave it there. Check. Move on. Let's see how this algebra first helps us with even more complex ones. Okay, so right here, normally I would think this is product, this is chain, and we got natural log, all kinds of stuff. But let's do the manipulation ahead of time. All right, let's define our spaces, our workspaces. There we go, there we go. Okay, so again, let's deal with this one layer at a time. So we have y equals, we can split up the product of those two things, natural log of x times natural log of 3x minus 1 to the 1/2. I could also drop this 1/2 out front. That's going to give me y equals natural log of x, or not times, this should be a plus, because it's times here, plus when we separate it, plus 1/2 natural log of 3x minus 1. Alright, super easy now. The derivative of the first term, 1 over x. That was too easy. Second term, we got this 1/2 constant multiple. But then the rest of this fraction, it's going to be the derivative over the original. Well, the original is 3x minus 1. And the derivative of that is just 3. So there we go. That really wasn't hard at all. So logs are not too hard when you use log properties combined with your derivatives and calculus and integration stuff. So let's look at the second one here, number 16. Let's change to red. So we got red here. I see a couple things. First, we could change this radical into a 1/2 power. So it's going to be x squared plus 1 over x squared minus 1. Now I could factor that denominator there. I don't really want to do that because it's really not that hard to deal with once I make this next step of separation. There we go. So let's drop the 1/2 because that's kind of like the most outside layer of this. We'd have natural log of x squared plus 1 over x squared minus 1. Now keep going. Y equals 1/2. Now that 1/2 is going to be applied to both these pieces, so I'm going to keep it outside here. Natural log of x squared plus 1 minus natural log of x squared minus 1. So there we go. Derivative. Constant tags along. It's just constant multiple rule. Inside here, we're going to have two fractions. And it's each time going to be the original part on bottom, so x squared plus 1 for the first one, x squared minus 1 for the second one, and the derivatives of each of those on top. So 2x for the first and 2x for the second. Excellent. That was like a piece of cake. Now, of course, you could simplify and other things like that, but for the most part, we get it. We get the idea that algebra first helps us. Whoa! Look at number 17. My goodness. So many things that we could break apart. Well, let's do it one step at a time. So here's what I'm first looking at. I see x times x squared plus 3 divided by cubed root of 2x squared plus 4. So I'm going to do y equals natural log of x. Now the multiplying, so the two pieces in the numerator, I'm going to add. So natural log of x squared plus 3 to the third. And then the quotient for this bottom piece means I'm going to subtract. So minus natural log of, we're going to run out of space there. Let's create some space. So this is still all like one line continued. Minus natural log of 2x squared plus 4 to the 1/3 power. We can change that cube root to 1/3. So I have three terms. Here's first, second, third. Let's go even further and drop those powers for the second and third terms. So that means that y is going to be natural log of x, that stays, plus 3 natural log of x squared plus 3. And then for the third term, it's going to be minus 1/3 natural log of 2x squared plus 4. Alright, so now I think we're ready to do derivative. And why? What tells me that? I see, with my little eyes here, single layers. These are polynomials, easy to do derivatives with simple one-step kind of power rules. And I've taken away all the outside layers. There's no extra stuff for me to deal with. So y prime, the first term, natural log of x, becomes 1 over x. The second term is going to be a fraction here. We have the constant multiple 3, so we'll have that 3 there. Then, it's going to have the original on the bottom, x squared plus 3, times the derivative of that on top, which is 2x. The third term has minus and a 1/3. But again, we're just going to have a fraction with the original on bottom, which in this case is 2x squared plus 4. Squeeze that in there. And the derivative of that on top of it. So the derivative of 2x squared plus 4 is 4x. Okay, so if we needed to simplify, we could, but let's see if I can rewrite this just slightly more clean. Squeeze the front a little bit. 1 over x plus, we'd have 6x over x squared plus 3 minus 4x over 3. We can go ahead and distribute this 3. We'd have 6x squared plus 12. There we go. Check. Alright, now I think we're going to see some applications of this. Not just a direct question, but more, how do I kind of deal with additional details? Well, let's look at the first one. It says 18 here, number 18. It says x squared minus 3 times natural log of y plus y squared. Okay, so here's what my eyes are kind of focusing on. I have x and y mixed. What does that tell me? That tells me that I'm going to be doing implicit differentiation. And for implicit differentiation, what we want to realize is that it's like a chain rule, pretty much, where the inside layer when the inside layer is y, that chain, the attached chain, we have to put a dy dx on top of it, or not on top of it, next to it, attached to it, multiplied. All right, let's give ourselves some workspace. See if we can stay inside that line. So the first thing, let's just do each term. So the first one, we have x squared, and the derivative of x squared here is going to be 2x. No big deal. The second term has a constant in it, so that stays, the minus 3. Natural log of y. Well, we would treat it like, natural log of x, so it's just going to be 1 over y, but then we multiply by the derivative of y with respect to x, which is just dy dx. Okay, good so far. Now the fourth term is y squared, the derivative of that, pretty easy, 2y, but because we took the derivative of y, we have a chain here, dy dx. And then the last term, 25, and goes to 0. Alright, so I see this second term and third term here on the left both have dy dx's in them, so I need to group these, and I need to move, I need to get those on one side and the non-dy dx terms on the other side. I'm going to go ahead and move the dy dx terms. So let's move those over to the right. We'll leave the 2x over here. That means over on the right side we're going to have 3 over y plus 2y, all of that times dy dx. I'm going to go ahead and factor out the dy dx. Now that I'm here, I really just need to divide by this big complex term here, which would really be 3 over y plus 2y. I got to divide by that on both sides. 3 over y plus 2y. Now I have dy dx equals 2x over 3 over y plus 2y. Okay, so not too big a deal. Pretty easy to follow as long as we remember the catch that whenever you're taking a derivative of y, you need a chain rule, dy dx. Pretty cool. All right, now let's look at this this next one. It says find the relative extrema of this log function. Okay, so the first thing that I'm thinking of is relative extrema. What's that cluing me into? Well, when I hear the words relative extrema, that usually means like a max or a min, local max or local min, which means I got to figure out when y prime changes sign. And y prime changes sign often when y prime equals 0, or the derivative does not exist. So that's what we need to look for. So I look at this, and it's not as hard as you would think. Some people would kind of freak out about this one, but it's really just a polynomial single layer here. If I were to say u equals x squared plus 4x plus 6, du dx, the chain, is going to be 2x plus 4. No problem. So let's work it out here. We'd have y equals x, whoops, let's take that back. The 1 over x squared plus 4x plus 6 times du dx, and I'm just going to put that in this numerator here, which is 2x plus 4. Okay, so a couple of things. We got x squared plus 4x plus 6. That doesn't really factor. And let's see, I'm not even sure if that would have an x-intercept. I don't think it does. And you could check that using like quadratic formula and discriminant, but I'm pretty sure there's no real, this does not equal 0. So x squared plus 4x plus 6 does not equal 0. There's no way to really get that, even with some fancy square root. Now what's cluing me into that, you guys are probably wondering, here's how you could check if you did like negative b plus or minus square root b squared minus 4ac. This piece right here, if that is negative, which in this case it would be, because we got 4 squared, which is 16, minus 4 times 1 times 6, which is 24. So that's a negative number, which means these are imaginary roots, which means there's no x-intercepts. That's pretty much what's happening. So that was a long explanation to say y prime does not exist is not one of our options. So we really need to look at y prime equals 0. That would be the numerator. By the way, this is y prime. Should have labeled that correctly. That means I really just need to look at the numerator of this fraction. So 0 equals 2x plus 4. Shouldn't be too hard from here. You just kind of see what x would equal. Well, x equals negative 2 if you do the algebra. Move the 4 over, it becomes negative 4. Divide both sides by 2. X equals negative 2. So it says find the relative extrema. Well, that's where it would be. X equals negative 2. Do I know that it changes sign before and after negative 2? I do, and the advanced reasoning method here is if you look at this function itself, it's linear, it's got a linear numerator. That means that it's going to change value at its x-intercept. Now that's some advanced reasoning there. If you don't trust me, go ahead and graph it and you'll see. But let's go ahead and move on to 20, because what we did, we just confirmed that we found the relative extrema, just dealing with derivatives. Now let's do another version in working with derivatives, and that's the equation of the tangent line. Okay, so, oh, there we go. I hope that didn't interrupt too much. I erased a few things, and now I have some more space on this video. So it says find the equation of the tangent line. So trigger here, tangent line. Tangent line should keep in mind, the point slope form equation here where we have y minus y1 equals our slope times our x minus x1. And they actually gave us x1 and y1. It's right here, x1 and there's our y1. So we have those two numbers. This is a 1 and this is a 4. So the only thing that's missing is slope. And to find slope, this is really the derivative. So y prime, let's take that back there for a second. It's y prime when x equals x1, which is in this case 1. Alright, so let's take the derivative. Y prime. The derivative of the first term, 4x squared, is just 8x. And the derivative of the second term here, natural log of x, is 1 over x. Alright, so we put those two things, we try to evaluate it at x equals 1. So y prime at x equals 1 is 8 times 1 minus 1 over 1, which is 7. So that's my m. So let's put the pieces together. Y minus the y value is 4 equals 7, my slope, times x minus the x value, which is 1. Tangent line. Too easy. Too easy. Alright, so this isn't really, what it's saying right here, this isn't a necessary skill for the AP exam. They're not going to check that you specifically know how to do this, but sometimes it's helpful in taking derivatives. So what are we looking at here? We're taking the natural log of the hard expression in order to take advantage of log rules. So when I see this, I see y equals a big complex function. Now there's no natural log here, and that's kind of the point. So it's not here yet, but I can apply natural log to both sides the same way that you would do any other kind of step in algebra where you manipulate both sides of an equation equally. That would change this into natural log of y equals natural log of 2x minus 1 cubed over this other stuff. X squared plus x plus 1 to the 1/2. Okay, so we can do that. And why would we want to do that? Because this natural log applied to all these pieces makes it so that we can split them up, deal with them a little bit more easily. But then we got this natural log of y over on the other side, and that is going to change some things around, but it's really going to help us out for all these complex pieces. So let's first simplify this equation with some log rules. Well, if we start with, how about the quotient, then we'd have natural log of 2x minus 1 to the third power minus natural log of x squared plus x plus 1 to the 1/2 power. Now we can drop these powers out front. There we go. So that's, and of course this is equal to natural log of y. So one more step of simplifying here, we'd have 3 natural log of 2x minus 1 minus 1/2 natural log of x squared plus x plus 1. All right, now that we have all that, we could take a derivative. It's like an implicit derivative because we'd have, we got a mixed function with y here. It's not just simply dy dx. So the derivative of natural log of y is really 1 over y times dy dx. Now for these pieces here, we'd have 3 as a constant, so that stays. The derivative of natural log of 2x minus 1 is really going to have a 2x minus 1 on the bottom, and the derivative of that on top, which is 2, minus, now again we have more fractions. We have the 1/2. We're going to have this original on the bottom, x squared plus x plus 1. The u is on the bottom, 1 over u, times its derivative on top, 2x plus 1. So I have all this, and then somebody's probably saying, okay, that still doesn't look less complex, but here's where it gets simplified. So now we just multiply by y on both sides. You're like, oh, look, now I have dy dx. But we have this y, and that's kind of weird. But wait, we know what y is. So all I got to do is plug that in. And in this case, our finished answer would be 6 over 2x minus 1 minus 2x plus 1 over 2 times x squared plus x plus 1, all times the original function, which was 2x minus 1 cubed over square root of x squared plus x plus 1. So there we go. Easy peasy. Lemon squeezy. There's your derivative. Alright, so that's it for this video. Thanks for joining us, and we will see you in the next one.